Okay, well, while people arrive, so this is the last lecture. Yes, yeah? Where have we been and where are we going? So the first lecture, Evolution of Conflict, introduced Hawk-Dove game, and the basic mechanics of evolutionary stability analysis and simple games. And I did cooperation. Simple cooperation games like the games in the first lecture, but you saw some more complicated population dynamics. In the third lecture, we did reciprocity, right? How to model repeat games, how to think about basic contingent strategies in repeat games, how that changes outcomes. Yeah. Monday, this week, what did I do? What was it? Covariance stuff, right? So it was kinship, right? So covariance, genetics, price equation, that sort of stuff. The impact of if you interact with close genealogical relatives, why might that help nice strategies to evolve? And today so there's a scaling up here is the idea. Yeah. So we start with simple dyadic conflict, individuals who are unrelated. We look at cooperation in the same context. Then we add persistent relationships and see how that changes, but we're still at the dyad. It's not even the minimal definition of a society in sociology and anthropology is 3 people. Yeah, do you need a triangle? There's this old quote from a German sociologist about this, right? 2 people, that's like a relationship, and 3 is a society. Yeah, it's much more complicated as soon as you've got 3. So I think it was Zemmel, actually, is the German sociologist who said something like that. And so up to 3, we don't even have a society yet, right? We've just got dyads interacting. But now we start talking about kinship, even though the interactions are still dyadic. I haven't showed you any games that are like mass action games. Those exist. We're still in just dyadic interactions. But individuals are embedded in families, and that has consequences for lots of stuff about how selection works. And that's the point of studying kinship and inclusive fitness. Yeah. And now we're going to keep scaling up. And the conceit is today we're going to model societies. There'll be more than 3 individuals. But not really societies unless you squint really hard, but there'll be societies in the sense that there's now explicit population structure that's going to matter. I'm going to show you some examples of how to model that when there's individuals don't live in just a giant, well-mixed vat of life and interact equally with all individuals in it, but instead there's spatially explicit population structure, and that influences who you interact with, and that can have big effects on selection. I want to show you a couple of examples of models like that. These types of models where there's spatial structure, the forces can be really strong. The forces of migration and selection on things like dispersal can be very strong. That's the game. That's the idea of what we're going to do today. And I want to show you 2 models, and I'm going to take my time developing the first because the second model we get to reuse the first, basically. I get to modify it. And that's how a lot of the modeling in the sciences works, is you study other people's models and then you modify it a little bit and learn something new. So it's actually, the whole game of modeling is easier than it seems because you don't invent the whole model. Right? You start with the existing structure and explore changes in it. Okay. Good? Questions? You're in for the rest of the hour and a half. Okay, so I'm going to start with modeling societies. I'm going to start with a classic model in evolutionary ecology, which is about dispersal and migration, and it's actually based on plants. So I keep hinting in the previous lectures that plants have social behavior, and they do, and there are people that study this. Yeah. We move really fast from a plant's perspective, but they have behavior, right? They're just really slow. We're like buzzing around them, burning out. Yeah. And the classic model comes from the interests of ecologists, where they observed that in many plant species, a vast majority perhaps in some groups, seeds are programmed to disperse quite far from the parent, and this seems like a paradox, or seemed like a paradox to lots of ecologists, because most of those seeds they know from experiments are going to die. Why program your babies to disperse out really far from the home site? The home site is safe. You grew up there. Yeah, you know that you can survive there. You have produced seeds at this site. And now you're going to program all your babies to go off unaccompanied into unknown locations where they will be devoured. Almost certainly. This is what happens to almost every acorn, right? And think about it. Poor seeds out there being killed constantly by vicious birds all the time. Squirrels, worms, everything eats seeds, right? They're delicious, right? If they didn't want to be eaten, they shouldn't be so delicious. Yeah. So this was a kind of classic paradox in trying to theorize about the evolution of life history in plants. But the dispersal problem, maybe you don't think of seeds as being dispersers, but there are traits that the parent puts on the seed jacket, like wings, that can make them disperse. There are lots of grasses that make little parachutes and fluffy things. You can tell I'm a botanist, fluffy things that you attach to seeds so that they actively disperse. And of course, in animal societies, there's lots of dispersal away from natal groups. Quite often, it's one sex more than the other. Right, so like in primates, in many, many primates, males are the dispersing sex. They leave their natal group when they reach sexual maturity, or they're chased out is actually often how it works. Sometimes they appear to leave on their own accord. Other times they are expelled through a gentle program of youth enrichment, right? Kicked out of the group where they must find another. In other species, it's the other way around. Males are the so-called philopatric sex, and females disperse. That's more common in birds, I believe. And you get all kinds of mixes of these things. You get cases where both sexes disperse, but there's lots of dispersal from natal groups. So the inspiration of this model is plants, but I don't think it'll be hard for you those of you who have an animal bias, to see, first of all, get better. But second of all, it will not be hard for you to develop an interest in the model anyway. What we're going to imagine is an environment in which there is a ring of sites that individuals can occupy. So the circles on this line are places where a plant can grow up. We'll call them sites. And the carrying capacity of each site is one plant. So these are small sites. This is how ecologists work. Yeah. And we're going to be interested in modeling the population dynamics. So we're not just interested, we will model the population dynamics when there is dispersal of seeds between sites. So offspring are produced at a site, there's an adult plant, it produces K seeds. K is just the average brood size. If it was animals, we'd call it brood size. It's the average number of seeds that are produced. We're going to let the letter little v be the probability that a seed disperses and leaves the natal site, catches the breeze, whatever mechanism you like. If you prefer to think about animals, it's just whether they move or not. And we're modeling the ecologist's intuition. And the ecologist's intuition is that dispersal is costly and risky. There's a chance that you don't survive dispersal, and therefore you can't occupy a site. Shouldn't you just stay where you were born? Because you know that's a viable site. So we're going to impose a cost on dispersal, which is the probability that you survive is less than 1. Survive. Survive dispersal. So the probability that you land anywhere. It'll become clear when I start writing expressions. You'll see exactly, implicitly, the definition. Good so far? This is basically the whole model. And now I just have to take these symbols and arrange them into a fitness expression, just like always. This is the game. Yeah, you start with the story that inspires the modeling scenario. We want to know if some argument is correct or what its quantitative details are. In this case, what's up with all this dispersal? Let's make a model in a structured environment where there's dispersal, and we're going to study the evolutionary dynamics of V as a heritable trait. We're going to let that vary. And so the first thing to notice about this before we start writing down expressions is this can take any continuous value between 0 and 1. So this is unlike the previous models in the previous lectures, right? Because now we have an infinite strategy space. Yeah? Before we had, say, very simple, discrete strategies. You were tit for tat or not. Yeah, you were hawk or dove. Couldn't be a little bit hawk. Right, a little bit dove. Now we're going to do a continuous strategy space, and this is easy. I'll show you how to do it. I'll wave my hands a little bit, but there's mathematics, or the full mathematics are in the notes, and but it's actually quite easy to study continuous strategy spaces. It's not any harder than studying discrete ones. It makes people nervous, but I'm here to tell you it's perfectly fine and show you some examples of it. It's also a lot more compatible with what we know about genetics and the regulation of behavioral traits, right? Is that they're massively polygenic, and any particular allele is having any effect. Yeah. Nick Barton has this great paper where he argues that if an organism could have any genome structure it wanted, it'd want one such that every trait is coded for by an infinite number of alleles, and each of them has an infinitesimal effect, and that would be the optimal genome structure from the efficiency of natural selection perspective, right? And so I think to a first order approximation, that is the human genome, right? That basically the whole genome is involved in every trait, like height, right? Like the whole genome to a first order approximation is involved in height, that sort of thing. And most alleles have tiny effects on traits. It's still a mathematical approximation. It's the opposite extreme from what we've done before, but mathematically it's not any harder to do. That's the good news. Okay, this is the setup. Questions? To write a fitness, this is the goal. We're gonna imagine. Let's see how I should do this. Let's start by just writing down the fitness for any old strategy V that's a common type in the population, right? So in order to do that, you have to consider all the possible sites that they could land in. So we're going to think about, there's just some site here that I've zoomed out, and we're going to think about there's one adult plant at this site, and it's going to produce some seeds, but there are going to be seeds arriving at the site from all the other parts of the environment too, and then the seeds will fight. Yeah, through some unspecified mechanism, and one of them will grow up at this site to produce seeds of its own. And we're gonna do the accounting for this. And we're gonna start just by writing out which seeds end up in the Thunderdome, as it were, right, in the arena at the end. Thunderdome's an old movie. No one here knows this, right? Mad Max? No, okay. But so the first thing is there are going to be seeds that we could call home bodies that stay home and do not disperse. And how many of them are there? Well, there are K seeds produced at the site. A proportion V of them leave. So let's write those, right? So here are the ones that leave. So V, K are leaving. Leaving the site. So these are above the K seeds produced by the adult at this site, a proportion V leave and go to other sites. We'll count for them later, right? They're still out there, but they don't land here. That's the point. They land elsewhere. Yeah. Oh, I should say one last thing. Let n be the number of sites in the environment. I'm going to let this be large, but I want to write down expressions so that they're specific to n. And at the end of the lecture, so in this model, we're going to look at big N, an environment with lots of sites. At the end of the lecture, I'm going to look at one with effectively a small number of sites. And you can see the difference. Okay, but let's get this logic. So VK leave. Also, there's just a chance P that they survive the experience, right? They'll land. So on average, VKP of these homebodies settle at some other site and get a chance to compete for it. Yeah? We're going to deal with them in a second. But this is the home site. So the homebodies, it's 1 minus VK. Yeah? Because it's the rest, the ones that stayed. Does this make sense? This is the whole model, basically. It's just writing down these things. There are immigrants. How many immigrants settle on this site? Well, you have to think about these individuals from the other sites, right? So these are the local offspring who disperse. They don't come back. They settle out somewhere else. But all the other sites are also producing these assholes, right? And so, sorry, this is the nativist perspective on the model, right? And so they're good. Some proportion of them settle out. Each of the other sites is producing VKP of these dispersers that are in the disperser pool, and they're going to settle out at random on all the other sites. This is an assumption. We're making it a global dispersal. You can make a version of this model which is local. I think I do this in my textbook as I do the local model. But I'm going to teach you the easy one where we think about it globally, and you can get the intuition that way. So we've got VPK, and there are n-1 sites producing VPK. Right? It's all the other sites. This is your site, and you send out your dispersers. All the other sites are sending out dispersers, and there are n-1 of those. But they settle out at this side only n-1 at a time. Right? Because from their perspective, you're just another site. And there's n-1 sites that their offspring are settling out at. And so you just get a fraction on average, n-1 of those dispersers. And you might notice it's very nice that those things cancel, but I'm not going to cancel them because I want you to see the concept. Okay? Does this make some sense? This is what happens on average. There's a distribution. If you wanted to make an agent-based version of this model, there would be distributions. But we're going to model what happens on average. It's a good approximation to what happens. Yeah?
So the -1 is the site that they came from?
This -1 is the number of other sites. Yeah, it's all the other sites. So it's the number of sites that they came from, right? So there's all those other sites, n-1 other sites. They're producing VPK, and there's n-1 of them. So the total disperser pool is n-1 VPK. This n-1 is all the places they could land, and there's just a chance 1 over n-1 that they land on you. Yeah. Does that make some sense? Okay. The other thing is there's all the other sites. So if we're going to write a fitness expression for the individual at a home site, their success, I can do this, yes. We want to say that the probability that they, I'm going to say win home, probability that they win their home, meaning one of their offspring inherits the home site that they were at. Right? You're imagining these are annual plants. This is an ecologist's favorite sort of organism. An annual plant grows up, makes some seed, and dies. Yeah? It's a full life. Yeah? And so it's different than a plant that is perennial and lives for multiple years and produces seeds multiple times. You can do the perennial model too. It makes it more complicated because now parents compete with their own children to occupy sites, which is true in nature. Yeah, the parents here know what I'm talking about, right? Just to compete to occupy your own Wohnung, right? So we can write this down from this expression. The probability you win the home is 1 minus VK, right? It's your competitors at the home site over all the competitors at the site. So 1 minus VK plus VPK. And that is 1 minus V over 1 minus V plus VP. I just want to get the logic across. There's nothing to learn from this expression yet. It's just a bunch of V's and 1's. Yeah. But to understand the logic of how I wrote it down is what I want you to get. Yeah? So if I want to know the chance any one of these homebodies wins the site, I want the number of homebodies over the total number of seeds at the site. Right? And that includes the other homebodies. You can start to get a hint of what is revealed by this model about why dispersal is favored. And it's because you end up competing with all the other seeds at the site, and if they're your siblings, this is bad for the family growth rate. Yeah? Does this make sense? Just the logic of it? We're going to do the other sites now, and then there's going to be this aha moment, I hope. Yeah.
I'm sorry.
Yes?
So, in this case, the problem is that the homebodies thrive in their home and not in the...
No, there's no advantage that homebodies have at their home site. We're merely trying to calculate the fitness, the expected fitness of an individual in this population, so that we can do invasion analysis. Then we're going to calculate. What we're doing right now is just the fitness of a common type in a population where everybody has the same strategy. Then I'm going to introduce a mutant, and this is biology, so we like mutants, right? We hope for them, yeah? And we do. That's like the mutant in a biology textbook is what you're like, yeah, mutant, right? It's a positively valenced word in biology, mutant. Right, biologists? I think this is true. Every time I read the word mutant in a biology book, I'm like, yes, go mutant. And so we're going to introduce that and then modify this expression for the mutant, and then we're going to do invasion analysis. And that's the program. Right now, there's no difference, competitive differences at all. All seeds there's some variation in their competitiveness, but it has nothing to do whether they're homebodies or not. Yeah. Is that a question?
Yeah, I was going to ask for the seeds that leave.
Yeah.
P. Why is the P included in there for the X?
Because that's where it applies. It's the cost of dispersal, the chance you survive dispersal. Yeah. So the P is the probability you manage to land any place. So you're only a competitor if your biased coin P comes up heads or whatever. Yeah. So then when they enter here, they've survived. But there's 1 minus P fallen heroes out there, unmarked graves of seeds in the wilderness. And they didn't manage to land anywhere, or they're in the bellies of squirrels or whatever, murderous squirrels. Yeah. Good? Does that make sense? Questions like that are very welcome because even though there's only 4 symbols, they get stirred together in interesting combinations, and sometimes the biological reasons for the same expression are different, like this n-1 and this n-1 mean completely different things. It's just how reality is. The universe is hostile to human life, and I think it's a great victory every morning when I wake that we exist at all. Right? And science is possible, right? It's just a miracle that this is the case. Okay. This was progress. It doesn't feel like it yet, but in a moment I hope to show you that this is progress. We need to do the other kind of site now. I'm going to do some erasing. So now we're going to imagine all those other sites you could colonize. So you get fitness. Take the perspective of one of these adult plants at a site. You get fitness through your own seeds that reoccupy your site, and that's what we've just written up there. But the other component of your fitness is your successful dispersers, right? And there's n-1 other sites out there. So this could be a big part of your fitness. Yeah, we haven't written that down yet. So let's model that site. There's some other adult here that you don't care about, and you want to crush them with your children. Yeah? And so your children come in. How many of your children settle on this site? Well, you're producing VKP dispersers total, and a fraction n minus 1 of them will land at this site. Yeah? Does that make sense? There are the dispersers from all the other sites too, other than this one. And they are also producing VPK n minus 1. And there are n minus 2 of those sites. I'll walk you through that. So these are just like, these are the enemy's invaders. These are your invaders. These are the enemy's invaders. Yeah, there are n minus 2 of those enemy sites. Why? Because we're taking out your site and we're taking out this one. So it's n minus 2. Right? There were dispersers from this site, but they're gone. Instead, there are homebodies you must defend against, or my homebodies to defend, and they are 1 minus v, k in number. Make sense? All right, that's the whole model. So probability. The probability you win fitness at the away games, so to speak, we're going to write a probability, and then we're going to multiply it by the number of sites like this. So the probability is VPK n minus 1 over VPK n minus 1 plus 1 minus VK plus n minus 2 VPK over n minus 1. So I've just put your invaders over everybody. Yeah? And this is the expected number, or the expected number of successful seeds at this site. And we're going to multiply this by n minus 1, because there are n minus 1 of these sites. Okay. This n minus 1 and that n minus 1 cancel. That's very nice. Yeah, and all the k's cancel. Let me go ahead and cancel all the k's. Good? Yes, question.
Why do we have n minus 1 and not n minus 1? Why is it necessary?
Why do this one? Yeah, because that's how many away sites there are. So you're a plant. You're an adult plant. You've had a successful life. You just produced some seeds. You produce VPK dispersers that go out, and there are n minus 1 sites that they're scattered across. And so at any particular site, this is the chance that they win that site, and there are n minus 1 of those sites. It's yeah, redundant, okay, but we have to do it. It's necessary. And yes, it results in a cancellation, but that's not an accident. That's why you intuit it as redundant. But the definitions in each part require it, because they're spread over n minus 1 sites, and that's why this n minus 1 is here. But then we have to multiply by the number of sites after right? So you do the calculation, assuming the spreading happens, and then you have to get the aggregate back again. And so that's why they both appear, and then they cancel, and you're like, why did Richard do this? It's like, well, it's because that's the definitions, and I want to develop the expressions for you. Yeah? Does that make sense? Okay. Now what I'm going to do is I'm going to assume n is large. And you don't have to do this. You can solve this model for any finite n, small n, and such. But I think the lesson goes better if we just let n get big for 2 reasons. It makes the expression simpler, and you can focus on the concepts, which is always the best thing when the first time you meet a model structure. It also lets me show you how to simplify expressions, which is an essential part of doing this sort of work, is doing approximations. When you're analyzing models, you often want to say, what happens if this variable gets big? How big? Infinity is a good number. It's my favorite. Yeah? Or if it gets small. How small? Negative infinity, also an excellent number. 0 is also an attractive number to let things go to. Depends upon the details of the model, but you want to analyze and understand the model by taking limits as the different variables go to extremes. And for population structure, it's often hard to solve for complicated finite population structures, so we let the population get big. When that's true, what happens to this expression? N minus 2 over n minus 1, as n gets big, becomes 1. Remember limits? Yeah, there was some time in your educational experience where you did limits, you blacked out, you woke up in a strange city, and you swore never to speak of it again, right? That sort of thing. Okay, well, it's back. No, you could have some exercise, and I'm not going to do it formally, but as n gets big, remember with limits, the constants go to 0 is the way you think about it. If there were a mathematician here, they'd be screaming right now about how I'm defining taking a limit. But this becomes approximately 1. And so this becomes VP. All right, I'm going to write approximately here. And this is 0. So it's just 1 minus VP. Isn't that nice? Yeah? Now here's the trick. The fitness of I'm going to call it the common type individual, is just the sum of these two things. Yeah? This is your fitness through the home site. This is your fitness through the away sites that you may colonize. Got this Led Zeppelin song in my head now. Immigrant song? Anybody know? Yeah. Led Zeppelin. It's an immigrant song. Come from the land of the ice and snow. Yeah, something like that. That's the official song of this model. Right. The invading Vikings. Yeah. Inspect this expression for a moment, right? What is it? Well, the denominators are the same. That's nice. Yeah? So what is this? Yeah? Over. Curiouser and curiouser. What is that? It's 1. Don't you love it when this happens? Now let's talk about redundancy, right? All of it was redundant. The fitness is 1. Okay, why did this happen? This is one of the things I love about modeling, is the futility of algebra. No, because this was not perhaps obvious to most of you when I started the model, but this has to be true. And so when you get a result like this, it's often good to pause and think, why is that the case? The average fitness in a population where there's only one type with a dispersal probability V is 1. Why is that? And that will be true for any V, right? We just did a derivation. This is true for any resident type, common type in the population, dispersal probability V, whether they have no dispersers, V equals 0, or all dispersers, V equals 1, their fitness is always 1.
Because population is constant?
Right, because the population size is constant. So at each site, at most, and inevitably, exactly 1 adult will be successful. So if there's one, imagine extremes, like you're the most successful adult ever, and you produce a bunch of dispersers, and they colonize all of the sites. But that means all the other sites have 0 fitness that generation. And so the average fitness is still 1. Right? Because there are n adults and there are n sites. The average must be 1. This was not obvious when we started the model, right? You get some experience with this and you see it coming. We have population regulation now in this model, which is much more realistic, but also typically harder to work with. And that means the average fitness is not in play. Natural selection does not produce adaptation in this model. I'll say that again. Natural selection does not produce adaptation in this model. It does not make the species necessarily have a higher population growth rate. Yeah. Because the population growth rate is fixed. Yeah. This is my complaint about intro evolutionary theory often, is that they act like natural selection is constantly making organisms better fit to the environment. But this kind of nonsense happens all the time. Yeah. Where actually fitness is fixed by constraints on life history and the environment. And natural selection is still doing stuff, but it's not making anything better. It's just giving you things to write about in your dissertation. No, I think this is really interesting. And this happens all the time with social behavior, and dispersal is a social behavior. Okay, it's just a consequence of frequency dependence. Yeah, that whether or not your offspring do well depends upon other people's offspring not doing well. Yeah. Is this good? I am on schedule. So now we're going to consider, all right, so the average fitness is 1. Natural selection is still going to favor, and I want to prove this to you now, is still going to favor a particular value of V. Even though average fitness is always 1. That value of V will invade and be unvadable by the others. It will be evolutionarily stable, and I'll show you how to prove that. But its average fitness, once it invades, will be 1. And the population will be equally well off as it was before. Yep, the treadmill of natural selection. Good? Okay. So let's redo the model very quickly for a mutant. What I'm going to do is I'm going to introduce V prime, which is V plus delta, which is a mutant. There's some mutant genotype out there, and it has phenotype V prime, again, not a derivative. And V prime is V plus delta, where delta is a number very close to 0. How close to 0? Close enough to 0 that if you squared it, you would call it 0. Yeah? So you could say d squared is approximately 0. So we're saying that there's a lot of, this is the kind of assumption you make when you want to say there are lots of loci that influence the dispersal probability, lots of traits on the seed or on the parent that can produce dispersal. Any particular allele, any mutation is going to have a small effect. And so we model these small, this is the really committed Darwinism view of it, where there's gradual, no major genes. And then we redo the model. So we think about the home site. I'm going to write an M for the mutant here. Their home bodies are 1 minus V prime, K home bodies. Yeah, V prime is it's a home body tendency for a mutant. They produce some dispersers, V prime, PK dispersers, and there are the standard invaders from the N-1 sites. Just like before. Right, so the fitness of a mutant through home sites, 1 minus V prime over 1 minus V prime plus VP. Good? This is the most minor modification so far. I just added a prime to things. But I added it in particular places. And this is the trick, is to notice that there's still the common type, because you're invading. Yeah? So all of the other sites have dispersal probability V, but your site has dispersal probability V prime. Setting this up because this is an invasion analysis, and we're writing down the expression for the fitness of an invader that doesn't interact with itself except at its home site. Yeah, it still interacts with itself through the population structure. Now we write how it does at a common site. So the common site homebodies, 1 minus vk of them. There are common type invaders. And there are mutant invaders. And the mutant invaders are v prime pk over n minus 1. Yeah. Oh, wait, there are dispersers here too, right? So yeah, those aren't in the expression we write, but they have to exist. Yeah, we honor them. So we add that up here. So we're going to get this expression. The probability you occupy this site, you've got this chance. So this is all going to be multiplied by n minus 1. And we get v prime pk n minus 1 over v prime pk n minus 1 plus 1 minus vk, or the homebodies, plus all of these dispersers. Yeah? Okay. I've tried to spread the logic of constructing these expressions by first doing it just for a population with only one type, right? And that's where we got these expressions. And now I have rederived them at light speed, but with primes. But the primes appear logically only in the places where we're thinking about the mutant and its seeds. Does this help? Yeah? I thought about doing it all at once and just starting with the mutant fitness, but that seemed cruel. Yeah, maybe it's also cruel just to do more. But anyway, hopefully this is clear. Yeah? All of these examples, I think the models that I'm teaching you are interesting in and of themselves, but I've chosen them because they're examples of styles of modeling. And I've tried to select ones that give you in each lecture a different impression of how we approach problems like this in the literature. So that's part of the interest in this model is that as well. Okay. And now we can look at the mutant fitness. And the mutant fitness is not always 1. This is what's interesting about it. All right, so this simplifies, right? So the fitness of a mutant is 1 minus v prime, 1 minus v prime plus vp plus v prime p. The k's all go away. I'm just going to cancel them. Yeah. And let n go to infinity. So this term goes away, just like before. This one stays. And this one becomes vp. Yeah. Now, how do you analyze this? This is an invasion fitness, so if it can invade, it needs to be greater than that fitness, which is always 1. So we just need to ask what values, for a given value of v, what values of v prime satisfy this expression and can invade. So think you through this cognitively, ignore the math, forget math for a second. The math here is trivial, you just take a derivative. So that's what I talk about in the notes. But it's important to understand why always when you take a derivative. Yeah? Taking a derivative is the sort of thing that Google can do for you now. It's a trivial piece of applied mathematics. But it's important to understand why you might want to do such a mad thing to a function. And in this case, conceptually what we're interested in is since v prime is defined as v plus delta, and delta is some small number, you can start cognitively by imagining v prime is equal to v. Imagine you're a mutant you're so similar to the common type that you are. We're going to start the analysis there. And we're going to gradually make you different, but it's easier to start there. You know at that point that you get a fitness of 1, and so does the common type. But now we ask, if you change your trait a little bit so it's bigger, so that V increases a little bit, does this expression increase above 1 or decrease below 1? And it could do either. It depends upon the exact value of V. Yeah, so walk it through conceptually, and then getting the answer is just a little bit of math. But conceptually, that's the trick. Imagine V is a very small number, like 0. Okay, and suppose that's not evolutionarily optimal. More dispersal would be favored. What that means then is when we consider values of V prime a little bit above 0, this expression will be above 1. Does that make sense? Because it'll be favored. That'll continue, then V increases, and as long as V prime that is close to V, but a little bit bigger than it, is still favored by natural selection, then this expression will still evaluate to be slightly above 1, up until some point at which no increase in V is favored by natural selection, and then your fitness equals 1 at that point. Or increases actually will have average fitness less than 1, and you will be at an equilibrium. The other way to think about this then is put yourself at that evolutionary destination that I tried to paint for you. Natural selection has done its job. There's an evolutionarily stable value of V in the population. There are mutants all the time assaulting the population. They have slightly smaller and larger values of V. But you're at the evolutionary optimum, and so this expression for those mutants always evaluates to be a little bit less than 1. Because there's a hill there in what's called the fitness gradient. That's the way to think about this. Or to make a cartoon out of it a little bit. You imagine, mutant fitness. There's some value of V, right? There will be some curve, and there's going to be some point at which increases and decreases are not favored. You get a hill, and that's the way these functions end up working. Yeah, through the local dynamics. And so whenever you learned at some point in secondary school or college that if you've got a function and you want to find out where it's maximized, there's this trick. It's called a derivative. Yeah, and there are various conditions and about the functions you can use on it and so on. But in this case, it completely works. Cognitively is the wrong term. Let's say ghetto conceptually. The way to think about what the derivative is doing is we could just take V plus delta and put it in here for V prime everywhere, and then just do the algebra on this. And every time delta squared appears, set it to 0. I'll say that again. What we can do is you can just put a V plus delta everywhere in this expression, so this becomes 1 minus V minus delta. Yeah, and this is V plus delta P, and then there's another V prime there. Replace V prime with V plus delta everywhere, and then cross multiply. The algebra is going to be a mess. I don't recommend it, right? Unless you've got a computer algebra system, and then you'll see. But it's like a page. I don't know. I did this in my office. It's like a page of cross multiplication and suffering. It's just factoring, though, right? It's the sort of stuff that grade children are made to do. It makes them obedient taxpayers. Yeah, but there's nothing you don't know. There's no tricks. It's just you cross multiply. Right, you end up with this giant expression because you've got two fractions and they have different denominators, and you've got a 1 over there, so nothing goes away. There's no zeros, right? It's just a big branching bunch of factor nonsense. Yeah, but then it simplifies. Every time you come across delta squared, set it exactly to 0. What this is doing is constructing a linear approximation of the change in fitness in the neighborhood of the common type. I'll say that again. This is constructing a linear approximation. Linear because we cancel terms of delta squared. That makes it linear. If you want parabolic, keep them, right? And cancel the cubed. You can construct an approximation to any level. This is actually a Taylor expansion. It's like all smuggled in, but this is those of you who know Taylor expansions. So we're constructing a linear approximation of the change in fitness in the neighborhood of the common type. So that's a good approximation when alleles have small effects and the trait is complicated. Yeah, that's the idea. But instead of doing the calculus, sometimes people are more comfortable just doing the brute force algebra and canceling the delta squareds. That's the same as calculating the derivative on this. And the technique, there's a box in the notes where I show you the derivative version. Does that make sense? And then you get an answer at the end of all of this. Yes, there is one value of V which cannot be invaded, is evolutionarily stable, and you can solve for it. And I'm going to call it V star for lack of, because everybody likes stars. Yeah. And it's 1 over 2 minus P. So, what does this mean? Well, first thing to note is that this is potentially a lot of dispersal. So, again, usually when you get a result, you want to investigate it at the limits of the variables that are inside of it and think about, because it's easier to think about extremes. So think about a case where P is 0, there's no mortality cost. P is the probability you survive. So P is 0 means you're dead. Yeah? What is this when P is 0? 1/2, which seems crazy, right? So you don't mean exactly 0, but as it approaches 0, this approaches a half, which seems like madness. But this is the original paradox from the ecologists. Why would you send your children off to almost certain death? And the answer is because if you keep them at home, they fight with one another. Yeah? But that's what happens in this model. You can keep all of them home, but only one of them can succeed at the home site. So they're also doomed at the home site. They're just doomed. Sorry, this is the way nature is for the poor seed. Yeah? So dispersal is not a great bet for them. You'd prefer something else like boarding school, but all you've got is dispersal. And so even if dispersal is almost certain death, so is staying home. Yeah? I can tell this bothers you. Good.
Yeah, but isn't this a world in which there's a mutant V prime that we're defending against? Couldn't you theoretically, if your probability of succeeding at the home base is just your seeds over all seeds,
yes,
more seeds in the numerator lead to a greater probability of success if you have 0? Well, I guess maybe does the P count for everybody? So the mutant invader has no advantage either?
Nobody has an advantage in fighting, right? Each seed is equally competitive in this model.
True, but if you had more seeds at home,
yeah, but only one of them can succeed. But only one of them can succeed, and so you can produce 100 seeds, but if they all stay home, your fitness is 1, guaranteed in this model. So you're wasting those competitors. And so what this evolutionarily stable value, and this captures your intuition, which I think this is, you've understood it, is it's a quantitative issue where you deplete your home warriors, even though you need more than one of them to compete against all the invaders if you want to keep the home site. But you also get fitness, but only one of them actually occupies the home site. So you're sacrificing all of them as warriors by keeping them at home and hoping one of them succeeds. And then the others are always sacrificed. So it will be optimal to send some of them out to compete at other sites, even though their chances of winning at those other sites is vanishingly small. In fact, the chance they even arrive at another site is vanishingly small. That's still better than keeping them all at home under lots of circumstances. That's what this model is saying. And it's because of the competition with your siblings at the home site is the problem. So the other extreme, let P go to 1 so that you always survive, and then this goes to 1. Yeah? Dispersal. Hell yeah. Awesome. Tons. So when this model came out, ecologists, a certain group of very nerdy ecologists, my people, got very excited because this seems to explain this previously puzzling thing about plant behavior, is how crazy into dispersal they are. To get at Connor's question a little bit more too, if you you can modify this model. I think this is a homework problem, not the one that's on the website for this course, but in my book. I have this model in my book too. And I think there's a version of it where we increase the number of plants at each home site. So then you're competing with other families at each site too, and that softens this effect. So as each site becomes more diverse, there are more individuals, the carrying capacity, you can just make it any number, make it 3. Then you get less dispersal as a consequence of that. Because you're competing less with your siblings at the home site. So you get more fitness through the home site. Does this make some sense? Okay. I still have half an hour, so I'm right on time. Good. No questions about this? Now, I want to do a version of this model where, which is based on...
What will be the idea?
What?
That will be the idea for the meantime.
This is the ideal. This is the only evolutionarily stable value in this model is V star. Yeah. And you can make the model more complicated. Like I said, I think in my book there's homework problems where we have local dispersal, so you can only disperse to your neighboring sites. So those are the opposite extreme of global dispersal, and you get a different expression, but the intuition is sort of still there. Right? The idea is you get a different evolutionarily stable solution, but you want to understand it as emerging from the same principles. And so solving variations of a model is often a way to understand the model. We end up doing a ton of this stuff in this work. What I want to do is another version of this model, which is based on fig wasps. So I want to model a radically local population structure to show you how powerful local population regulation can be, and its effects on potential effects on behavioral traits. And the model here is fig wasps. I don't know how many people here eat figs. You like figs? Yeah, figs are great. Yeah? Okay, so you may know already, and I hope you do, and this is not news to you, that figs are fertilized by wasps. This is... they're commensal in this regard. Every fig in the wild has typically its own specialist wasp species, at least one. And the life cycle is, so a fig is an inverted flower. It's not really fruit, it's an inverted flower, and on the inside there are flower bits. And wasps get in there and crawl around and eat and live basically their whole lives inside of figs. So females disperse from a fig after they're born and they grow up. They leave a fig, right, out of the world. They find another fig, they crawl inside. They meet somebody special. No. They lay eggs. The eggs hatch. The eggs are male and female inside the fig. The males mate inside the fig and never leave. Males are wingless in fig wasp species. Their whole life is spent inside the fig. It's the only world they ever know. Yeah, but the females mate, get fertilized, fly out, find another fig, and the cycle of life continues. Fertilization happens because this is how the pollination works. It's the females moving from fig to fig does pollination. Isn't it wonderful? If you eat commercial figs, there's a wasp-free version of this life cycle, I'm told, that in big industrial fig production is now enforced. So, but you can still find, if you're lucky, dead wasps inside your figs. It's harmless, it's extra protein, and it's how nature intended the fig to be consumed. Okay? That's the story of the fig. Yeah? So if nothing else from this course, you have a new appreciation of figs. The wasps that have this life cycle are amazing, and they're kind of a model species in evolutionary ecology because they have incredibly skewed sex ratios. Very, very few males are produced in fig wasp species. Very few. And so the question is why, and we're going to make a model of that. You may know that sex ratios in animal societies are very, very strongly attracted to 1/2, or a ratio of 1, sorry. A portion of males is very, very strongly attracted to 1/2. And so if you had to make a prediction about any old random animal species about what its sex ratio is, you would say, well, about half of primary births are male and half are female. That would be an excellent guess. And there's a very powerful explanation for that. And so I want to, in the last half hour here, show you that explanation, give you an idea about how to model that. and also show you a fantastic case where natural selection favors something that's not a half, and that is a fig wasp, and why that would be the case. And the model will be basically the same as the previous one. Okay. So what we want to think about now is, just like in the previous model we thought about sites with plants, we're going to think about figs now. You see the resemblance. There's a certain number of figs in the environment. There's a fig. You're a female wasp. You've landed in the fig, and you've laid some eggs. What is the fate of those? What is the fitness you get through those eggs that you've laid? We're going to write an expression for that. So I'm going to say V little r. R is the trait that's going to be evolvable in this, and that will be the sex ratio of your offspring. I'm going to let little r be the proportion of, now I check my notes, the proportion of males, which is conventional, I believe. Or this is from the original paper. So the first thing is we're going to think about your fitness through your daughters. Yeah, we're going to count it up that way. Daughters are really, really important in evolutionary ecology models because they can reproduce. Yeah, and sons cannot. You say, like, sons can reproduce? Yeah, kind of. We're nice to guys and we say they reproduce, but come on. It's not really what's going on. Yeah, I say this as a father. Yeah, I know what happened. I was there. Yeah, and so daughters have this big effect because their contribution to lineage growth is much more direct. But what you want to notice here is that there will be no fitness effect of sex ratio on your own fertility. It can't. All we're talking about in this model is the proportion of sons and daughters within some brood size. I'm going to let this be little b in a second. When we talk about wasps, we talk about broods. So your fitness, variation in this trait R doesn't affect your fitness at all. You'll have the same number of kids, by definition, in this trait. But it will impact lineage growth through your grandchildren. And that's what we're going to count up, which is definitely a trick. And there is a principled version of this that I'm not going to do for you today, but I want to be explicit about this. We're going to count grandkids, and it's going to work. But that is not a principled thing to do. In this model, counting grandkids gives you the right answer. But in general, there's this thing you want to compute, which is the lineage population growth rate. And depending upon the details of the model, the mathematics for that is different. But if you've ever come across an evolutionary model where there are eigenvalues, that's what this is in spirit. It's the asymptotic growth rate of the lineage. But I'm going to do the simple version because I don't want to do matrix algebra. It just takes too long. In my book, when I do like a 10-week version of this, I do the whole thing, and I show you how to do this model with eigenvalues and eigenvectors to talk about the population growth. And all that's really important to know at some point if you get into this business. But so with your forgiveness, I'm going to do none of that. And I'm going to count grandkids, which makes me uncomfortable because it's not always the right thing to do. But in this case, it is. Sorry, thank you. I am Richard, and I'm trying to be better. So counting fitness through granddaughters is the first thing we do. So the first thing is, this is how many daughters you produce. Letter B is your family size, brood size. And I believe I took this notation from the original paper. This is a W.D. Hamilton paper. And then, how many grandkids does each of your daughters give you? B. Because they have the same expected family size as you do. Yeah? And so it's B squared. Exciting, huh?
What was R again?
R is the proportion of your offspring who are male. Ratio, R for ratio. So 1 minus RB is your expected number of daughters. Each of them has B. Your fitness through daughters is 1 minus R, B squared grandchildren. Then you have fitness through sons. You're going to produce RB sons. And then here's the thing about sons. They don't lay eggs. Yeah. And so you need an egg-laying intermediary for the fitness to be realized here. And so we need to model that. We need to model the probability that a male fertilizes a female in the fig. So remember, we're still in the fig. It's a very local dating market, the fig. Yeah, so we can count up the exact number of females. And so the chance any one of your sons fertilizes a female, will just have it be random. There's just random mating. Each of them could get B if they do a fertilization. And I'm going to let N be the number of females that lay eggs in the fig. N is not the number of figs, it's the number of females who lay an egg in the fig, lay eggs in the fig. In the literature, this is called the foundress number. There are foundresses of the fig. It's like a dynasty. Game of Thrones in the fig. Yeah, as they fight. They do fight in the fig. They try to kill one another. It's nasty in there. Yeah. I just want the notation to be clear. So there are N foundresses. Each produces 1 minus R B daughters. So that's the number of matings which are possible inside the fig, right? The number of fertilizations which are possible. And you produce, and there are NRB males. And so the expected chance that, this is the chance that a male gets a fertilization. Right? It's the sex ratio, the local sex ratio. And you can think about the action of this. Don't focus on the mathematical expression for the moment. Conceptually, this is the sex ratio, right? If there are very few males, then the bottom is smaller. And that means your chances, any particular male's chance, your son's chance of fertilizing is higher. Right? But if there are lots of males, then it's lower because there's more local mate competition. Does that make sense? The other thing to see from this is that your sons compete with one another for fertilizations inside the fig. Right? So this is like the home thing with the dispersing plants again. You've got offspring and they must compete at the local scale. Okay. There's some insight to get from this right away. We can simplify this. So this is B squared 1 minus R plus R. The N's cancel, the B's cancel. 1 minus R over R. Yeah? Lots of R. And if you have an American accent like me, it's very unpleasant when you say it over and over again. R, R, R. Right? But there's some magic in this expression. There really is. Let me try to, how am I going to draw this out? So the first thing I want to do is, again, our goal is to write an invasion fitness. So imagine an invader with trait R prime. Again, R prime is some sex ratio value that is close to the common type R. And I can just write that expression by putting the prime in the right place. Now I want to talk you through this. Yeah? You could have started up here, but I'll talk you through it. This R gets a prime because this is your daughters, right? This is how many daughters you produce. It's proportional to 1 minus R prime. This one is prime because that's proportional to number of sons you produce. This ratio does not have a prime in it because that's the population market you're playing against. Right? So your sons and daughters are in this marketplace of other individuals who produce a different sex ratio. And that's the sex ratio that you compete on. Does that make sense? Yeah. Notice that, let me draw it out for you a little bit. So if we're going to ask when this is greater than this, yeah, because that's invasion analysis. Stability analysis would be the reverse. When is this less than that? Because that would mean If we could find a value of r such that no r prime could invade, that would be the evolutionarily stable value. The same logic as before, and there's just a derivative to get it. The argument I try to walk you through in the notes is to think about changes in these ratios and what happens. And so this simplifies, you can simplify this question of whether the common type is stable when, hang on, when is VR greater than VR prime? And I write it like this. Yeah. So remember, delta is a small number. So all you need to worry about is whether it's positive or not. So imagine mutants that produce more suns. So delta is positive. It's a tiny number, though. This is the sex ratio that you're invading. Yeah? Or it's the ratio of daughters to sons. So imagine it's a small number, like 0. Yeah, so that very few sons are being produced in the population you're invading. This number then is 1 over some little tiny number. It's really big. So 1 minus some really big number is negative. So this is, wait. Does this work?
It's positive because it's 1 minus R.
Yeah, the mutant can invade, right? So this is the stability condition, right? So this is a negative number, so this is not true, meaning that the mutant can invade. The common type is not stable, right? This is the stability condition. It'll increase then, R gets bigger and bigger, until some magic thing happens. There's a special value of R at which something very special happens. Yeah, what's that value? A half. Yeah, you see what happens at a half? If we put in a half, the top is a half, the bottom's a half, this is 1, and this is 0. Now, this is the pivot point in the model. Add 0 then, this will never be satisfied, right? It turns out that the only evolutionarily stable value, once the population gets to a half, there will be no mutant, either with delta positive or negative, that will have higher fitness in this model. And this is this so-called Fisherian sex ratio result, which is that the evolutionarily stable value is a half. But this is a well-mixed population, and the implicit assumption here that I snuck past you is that your family doesn't affect this sex ratio. And I snuck that past you right here. I apologize, but this is all part of the magic show. Yeah? What happens if that's not true? What happens if n is a small number? I implicitly made n some big number that we didn't have to worry about. If n is a small number, so that it affects your offspring, then things change. So we can rewrite that. Yes. Yeah. So think about this expression. Let's do the fitness of r prime is 1 minus r prime b squared plus. What's that? Yes. So n is the number of foundresses in the fig. So I'm going to simplify this and say that expression for invader fitness. This is the action term. I'm going to write it f over m, just to make it cognitively easier to chunk so that you're not looking at more symbols, where f is the number of females in the fig and m is the number of males in the fig. And that gives you the fig sex ratio. So previously you were sort of saying, well, it's a really big fig. There's lots of foundresses. Your sons aren't competing directly. Let's rewrite the expression so that they are. So f, there are your daughters, and then there are n minus 1, 1 minus rb. Right? That's the number of females in the fig. This is, you're the mutant, as always. Yeah? These are your daughters, and then these are the n minus 1 others. And n could be small. It could be 2. Yeah? In fact, it will be super interesting when it's 2. It'll be interesting when it's 1 as well. 1 and 2 are very good values. Does this make sense conceptually? We're just counting up daughters. Your daughters, everyone else's daughters in the fig. Notice if n is large, then this term will be negligible, right? If n is large relative to b, and that's the typical Fisherian result. That's how you get the Fisher stable sex ratio at a half, is to let things be well mixed. And then the number of males, r prime b n minus 1 rb. Okay, the rest is just calculus. So I show in the notes, there's just one derivative to take. What we want to calculate is the rate of change in fitness as a function of the invader. We want to find some value of r such that the gradient of this is 0. I'll say that again. We want to assign some value of r such that the gradient of the invader fitness is 0. Why 0? Because that means that the value of r is an optimum, that there's no improvement. It's not increasing or decreasing in that area. Yeah. The invader is not better off. Yeah, as I show, I mean, this will make the Taylor expansion thing more obvious. That this is approximately equal to the resident type fitness plus delta times the gradient with respect to the mutant evaluated where the mutant equals the common type. That's an R. So this is the approximation that we're doing. So that thing that I did over here where you just do the algebra and you just substitute r prime for r plus delta and then you just do the algebra and cancel every time delta squared appears, that's exactly this too. It's the same math. This is just the version that looks like calculus. And since we're here in Leipzig where calculus was invented, we should bring it up as often as possible. Yeah. Here they make statues of you if you invent calculus. But this constructs a linear approximation of the change. Is what it does. So the invader fitness will be the resident fitness plus the change induced locally by its trait difference. So we want to find a value of r for which this part is 0. Yeah, and we can do that using this expression. And there's just one derivative to take. And the answer you get is that r star is n minus 1 over 2n. How am I doing on time? Good. So the math is not interesting, but if you're playing around with this model at home, I encourage you to graph these functions and get a sense about how the fitness gradient changes as you change the parameters in it. If there's some software you use that makes that easy, it's often when you're starting out with these models, it's really helpful to visualize the functions. After a while, you just wallow in the algebra and you're comfortable with it because you've got a sense about you're cognitively chunking the job. There's a workflow to doing this, working with these models where you're cognitively chunking pieces of it and you know the next steps you're doing. But when you're building those habits, it's good to visualize the steps in my experience, at least for psychologically healthy people. Yeah. If you get stuck when you're working through the notes, and let me know. I use Mathematica when I work because it just gets the boring math out of the way. I can do algebra. I don't need to prove it to anybody anymore, right? It's just like I'm done. And derivatives, like robots take derivatives. Yeah. Now integrals, now there's art. But but derivatives, it's just boring, right? And so I encourage that. Some software like Mathematica where you can have notebooks for models as you learn them. When I review modeling papers, I make a Mathematica notebook and I try to follow all the steps as best I can from the paper. That's how you learn how to do this stuff. So if you want to get into this literature like that. I encourage you, develop some workflow for yourself where you can mix in plots and do experiments with the expressions, because that's how you understand what's going on in these models. Okay, what does this expression mean? It's got one variable in it, n, so we want to let the variable go to its extreme values, so we can think about what this means. If I make n large, that should be the previous model, right? Because in the previous model, I snuck past you the idea that, oh, it's a big population and your own contribution to the mating market, dating market inside the fig is negligible. That's letting n be large. So as n becomes large, how large? How about infinity? I like infinity. Yeah, so this goes to infinity over 2 infinity, which is a half. I know. Wars were almost fought between Germany and France in previous centuries over the concept of infinity. I mean, this is like mathematicians just get into literally fistfights sometimes over these issues. There was some example, I'd have to look up the date, but there was some math congress in Germany in the late 1800s where literally a fistfight broke out over limit theory. So this Cantor and all that stuff, right? And the people had, very strong opinions about madness, like infinity over twice infinity is a half. I mean, it takes a certain kind of, a certain kind of confidence to believe things like this. No, I mean, the real numbers are not uniquely constructed, so, but they work most of the time. Okay, so that's good. That means this goes to the previous model as n gets big. That doesn't mean it's right, but that's a necessary condition for it to be right. Yeah, you know the difference. What happens when n is small? Well, as n goes to 1, which is the minimum, because we're modeling the fitness of a foundress, and so it's got to be 1, this approaches 0. So now we're going to get to exactly 0 because we haven't modeled what happens as male scarcity happens in the fig. In principle, there's a point at which a single male is insufficient. Yeah, to fertilize all the females in the fig, in principle. But we haven't modeled that. And so this can go to 0 and you can still have fitness in this model. But at some point, as it gets really close to 0, you're not producing any male in some fig, and then that's bad, right? So you'd want the proportion to be bigger. With that apology, you get the qualitative sense, though, that means natural selection favors very few males. It favors a female bias sex ratio. And the reason is that the males compete with one another. Your sons compete with one another for fitness. And so it's better to just produce daughters who aren't competing with one another, right? Because their offspring will be laid in other figs. Yeah? Males are fighting for a finite resource. Your daughters are not. Does that make sense? There are lots of variations on this model because when this result first came out, behavioral ecologists were arguing, it's a small group of behavioral ecologists were arguing about why female bias sex ratios existed in most famously in insect societies like wasps and bees and ants, right? They famously have these female bias sex ratios. And you want to imagine that, last century, especially the first half of last century, the mathematics of the evolution of social behavior was basically non-existent, and so the craziest verbal arguments held the day in journals. Just because you can talk yourself into almost anything without a mathematical model, in my experience. So when these models first came out as an explanation, people had their preferences for other explanations, and so variations of this model got made to put those other explanations in. And the story is that none of the other things produce female bias sex ratios, or people can't make models in which they do. So I think this is one of these cases where trivial model, just a little bit, it's all about accounting and counting up sons and daughters and producing sums, and a little bit of calculus at the end, but it has a big effect on changing arguments in productive directions, is what I would say about it. And since there's been a tremendous amount of empirical work on these insect societies and their female bias sex ratios. So for example, the number of foundresses should be associated across species with the sex ratio. That's a prediction here. And it turns out that's true in wild fig wasps. that the average number of foundresses in a species, the higher that is, that's associated with there being more males in the sex ratios. So these are wasps, so you can study them experimentally and in the lab, and you can count up all this stuff. And I think it's really cool. There's a let's say parallel intersecting line of research with fig wasps, which is about the male traits. So males actually compete, and so they're not inert about this. In some species of fig wasps, the males have big jaws and weapons, and they try to kill all the other males inside the fig. I told you it's nasty in there.
Yeah, siblings.
And they're siblings. That's right. Exactly. And yeah, one of the versions of this that people say it's not about. So this version I'm giving you, the explanation for female by sex ratios here is called local mate competition. Another explanation people used to favor is just inbreeding avoidance, right? So if your sons and daughters are in the same fig and there's fitness depression through them mating with one another, maybe that explains this, is that you're just having fewer sons to avoid the inbreeding effect. You can make that model, it doesn't work. Inbreeding induces very little selection in parents in most social models, actually. Stronger on the offspring. All right. The interests of the offspring avoiding inbreeding are usually stronger than the interests of the parents in getting their offspring to avoid inbreeding. From a pure genomic perspective, the details of those sorts of models are fun, but the point I'm just going to assert is that if you make a version of this model with that, you can put it in, you can mix inbreeding depression into this model, it doesn't change the results. Yeah, very much, which I think is interesting. Yeah. And there are lots of species which just routinely inbreed all the time, right? They purge themselves of their homozygosity and their homozygous recessives. Yeah, there's a fitness bottleneck you must pass through in such a life's history, but once you've gotten through it, it's a whole different world. Yeah. Questions about this?
Specifically, how can you get out of the
Nobody knows. No. Sex determination in animal societies, there are so many different mechanisms. For humans and for mammals in general, basically, as far as I can tell, no one has any idea how it works. No one finds modifiers. Aren't wild types with wildly skewed sex ratios in mammals. People debate whether, given the architecture of sex determination in primates and other mammals, whether there's even much possibility for this sort of system to work. People will argue that it's just not available given the kinds of mutations we can have in our sex determination system. Maybe that's true. There aren't really good examples of highly skewed sex ratios in mammals. I think that they should be possible, right? You get naked mole rats and other weird things, right? Where sex ratios can vary. It's really common in other groups of organisms. So some groups of organisms, I think mechanism matters is what I'm trying to get to. So like the Hymenoptera, in the Hymenoptera, wasps or Hymenoptera, sex determination is literally the difference between a fertilized and unfertilized egg. So females decide, I feel weird using the word decide with a wasp, but sure, wasps are people too. And females store sperm in a special organ, and when they lay the egg, they decide whether to fertilize it or not. But it's under physiological control, and there's a very precise control. And so, yeah, female wasps can fertilize every other egg if they like. They make decisions about this, and there's a fun literature about the female wasp as sex ratio optimizer because they've got this organ that lets them do it. I think and you find lots of adaptive sex ratio variation in Hymenoptera. I think not as a coincidence of the fact that they've got the physiology so that they can have it's very precisely controlled. Whereas in organisms like us, there doesn't seem to be any kind of precise physiological control, and we don't see much natural variation either. Yeah, does that make sense? Okay, let me wrap up here. This has been 5 lectures. Let me give you the tour again, remind you. The topics are hopefully interesting, but I've tried to give you a sense too of the modeling techniques. And in every one of these model examples, we start by telling a story about the biological scenario and writing down consequences of the behavioral options. in the population. And so in the simplest models, that was a payoff matrix. In this model, there was no matrix to write down because there were multiple routes to fitness, and so it already got more complicated, right? You've got fitness through your sons, through your daughters, through your dispersers, through your homebodies, right? These different kind of buckets of fitness that can lead to population growth, and so the expressions get more complicated, but the strategy is the same. That's what I want to get across to you, is communicate the structure to it. And implicitly, all the models are analyzed or solved the same way, even though they look a little different. We're comparing invader fitness to resident type fitness, always, in these cases. And the mathematics may look a little different all the way through, but that's the story. And if you look at more models in this area, you'll find that the literature has a big mix of all of these techniques I've showed you, and the thing that is different that I haven't showed you much of is games with more than 2 players. Yeah, so this last lecture was also an attempt to maybe atone for some of my sins. Is who are the players in this game? Well, it's all the individuals in the fig. So you can't represent this game with a matrix, right? Because there's too many individuals involved in the payoffs they get. Or maybe you could. I say that, and then a student will go home and write it down as a matrix, and it will make sense. But you're not constrained to think inside the 2x2 matrix. You want to think about the biological scenario, all the individuals who are impacted by your behavior, all the individuals that impact your fitness through their behavior, and account for those effects inside your payoff expressions. And if you can do that, that's the storytelling translation part, then the analysis is almost automatic. Your workbook can do it for you. Yeah, but it's the setup is the creative part. It's like writing science fiction when you do models. This is what I enjoy about it, because you get to translate the scenario into some formal representation and then animate it. Anyway, I hope this has been interesting to you and you've learned something exciting, maybe. And I appreciate your attention and indulgence. Thanks.